In the last two lectures, we have seen how particles interact with the matter. Uh, so, we have charged particles interacting with matter, then we saw how neutral particles interact. Today, we will talk about detectors and a little bit, very little bit of electronics that goes with it. So, particle detectors come in all kinds of shapes and sizes. However, the type of detector is decided by the physics goals of the experiment, and if, for instance, the detector is complicated, as is so in many of the high energy physics experiments, then of course it has to be simulated and the detector has to be optimized for the physics goal of the experiment, or maybe multiple goals of the experiment. We have seen broadly the kinds of detectors that we have, namely gas-based detectors, scintillator detectors, semiconductor detectors, cryogenic bolometers, and then there are many miscellaneous detectors which, for instance, there are detectors that use sound, acoustic signals to say which kind of particle has come. This is, for instance, there is an example in dark matter searches and so on. Sometimes, and actually in high energy physics is quite often, the detector also has a magnetic field because it has tracking detectors, and then that allows you to actually measure the momentum of the particle. Particle detectors that operate in real time produce electrical pulses which are usually very tiny. So, they have to be followed up by electronics before the resulting digital data can be sampled and monitored and so on and stored for a more detailed analysis. I have already talked about simulation. This is a very crucial step to make sure that you get the physics goals for which it was built. Now, let us come to the gas detectors. So, gaseous particle detectors can be operated in at least three types of regimes, which depend on the kind of voltages that you apply for a given geometry. And this is shown by a current versus voltage plot of a typical gas detector. So, for instance, if you have a parallel plate or if you have a wire in a cylindrical chamber and so on, then as you increase the voltage, the current saturates as is shown here. It increases initially and then saturates. So, this is the so-called ionization chamber regime. This is where once you have produced the primary pairs, then they are collected by the anode and cathode. So, the electrons drift towards the anode and the ions, the positive ions drift towards the cathode. If you increase the voltage, of course, the drift velocity increases, but you have not applied a voltage enough to actually make further ionization. So, there is no secondary ionization produced. If you increase the voltage further, as happens here, then of course, there is multiplication in the gas. So, the electrons that are drifting in between the, let us say, the mean free path in distances of order less than the mean free path, you can have an energy gain such that it will ionize the gas itself, and then from 1 you can go to 2, and of course, there are many of these primary electrons. So, you can get a multiplication of the the primary ionization. Thus, in a certain domain, it will be actually proportional to the initial primary ionization. Of course, it depends, the gain, so to speak, depends on the voltage that is applied. So, this is the so-called proportional regime where you have multiplication. If you go to still higher voltages, then of course, you have the so-called Geiger mode, where more or less the you can start out with different primary ionizations, but you will end up with the same kind of electron ion pairs at the respective electrodes. Okay. So, this is called the Geiger mode. So, in the Geiger mode, you do not have information about the primary ionization. If you go to still higher voltages, of course, then you get a corona discharge, and then of course, sometimes this is used in chambers called the spark chamber, but more often we have either the GM mode or the proportional mode or the ionization chamber mode. So, in nuclear physics, you have these ionization detectors which are used for heavy ions, energy measurements, and also finding out the particle ID. You can have carbon 12, carbon 13, carbon 14, and you want to separate them out. So this is typically at low energies, and this includes so-called Bragg peak detector. We will see that in a subsequent slide. You have also avalanche counters, which are parallel plate devices, which are used for very fast timing measurements. So there you make use of the time of flight technique. In high energy physics, you have these multi-wire proportional chambers. This was actually invented by Georges Charpak, who, again, we have a subsequent slide. He got the Nobel Prize for this, and of course other things that he did in the field of gas detectors. Then there are so-called drift chambers, and the most modern device that is used quite often in many of the high energy physics experiments is the so-called time projection chamber. This is the modern equivalent of the cloud chamber, a real-time electronic cloud chamber, you might call it, quote unquote cloud chamber. Okay, this is not really a cloud chamber. So, okay. So in gas detectors, as I said, you can have parallel and cylindrical geometries. So on the left is shown a parallel geometry where you have applied a voltage across the anode and cathode. You have the ionizing medium somewhere here in between, and the field lines are perpendicular to the electrodes and uniform across the area of this detector. So this is good for timing measurements, and also it is such a, not exactly this geometry, but a slightly modified geometry is used in the Bragg counter. On the other hand, you also have the cylindrical geometry where you have a wire and place at the center of a cylindrical chamber. So the electric field is small, so you apply voltage between this cathode and the anode. Electrons drift towards the anode, but as they come closer and closer, the electric field increases, because the electric field goes like 1 by r in a cylindrical geometry. And so then there is multiplication near the wire, near the anode wire, and you have gain, and that gain can be of the order of 10 to the 3, 10 to the 4 if you are operating in the proportional regime. And the advantage of this over the parallel plate is that because of the way it is constructed, you can apply relatively small voltages of the order of 100 or a few hundred volts, whereas here you have to, at least even for gaps as small as a few millimeters, you have to apply of the order of a few hundred volts. What is shown here is the ionization energies and the electron drift velocities for a few gases. Methane is a commonly used gas. There is a so-called P10 mixture where you have a mixture of methane and argon. Argon is also very commonly used. You have also isobutane. This methane has the property that it can catch fire if there is a leak and so on. Isobutane is less dangerous. Of course, it can also burn, but it is less inflammable than methane. And then there is also what is shown is helium. Helium is of course the largest average energy for ionizing and making an electron-ion pair. The drift velocities you can see range from of the order of 10 to 100 in units of millimeter per microsecond at all given at 1 kilovolt per centimeter bar. Okay. So charged particles which interact with the detector gas produce these pairs and move in opposite direction. The cylindrical geometry, as I already said, there is a modest voltage. The timing is worse in cylindrical geometry because it depends on where you ionize, where the primary ionization takes place, and then it can take a long time for the pulse to develop. So this is of the order of 10 to 100 nanoseconds, whereas in parallel plate geometry, especially when you have closely spaced anode cathodes, you can get timings as good as 50 picoseconds, but of this order, 50 to 250 picoseconds. However, higher voltages are needed of the order of kilovolt in planar counters. The multi-wire proportional chamber was invented by Georges Charpak. The idea is that you have an anode wires, many of them. This is just a fraction of that, just to show the principle, and then you have cathodes on either side. So you have electric field which is shown here. So close to the wire, of course, the field increases, and so you have multiplication here. But if a charged particle goes by, you can look at all these signals, and then you can say what was the what is the centroid of this trajectory, and you can get information about the trajectory. You can also have these counters placed in orthogonal geometry. So, you have one counter like this and you have another counter behind it which is perpendicular, the electrodes perpendicular to that, and so X and Y information can be got, and you can have a number of them. So, Sharpak made this invention, and it was extremely useful for particle physics experiments where you required large detectors of the order of few meter squared and many of them, so as to get a good efficiency for catching the particles that are produced in high energy physics collisions. Okay, for that of course he got the Nobel Prize in 1992. Then I talked about the Bragg curve earlier, sometime back. Basically, it is something that, when a charged particle moves in matter, it slows down. So, the d by dx increases, and then there is a so-called Bragg peak, and then of course, the d by dx goes down. So, this is characteristic of both the energy of the particle as well as the m and z of the particle. So, this is a detector which was built at the Tata Institute, and this is the corresponding paper. So, Satyajit Saha, Agarwal and so on. And then this shows the configuration where when a heavy ion comes in here and stops somewhere, you get a you get a ionization profile like this, and because of the drift, and you have measured the drift time with respect to some other time reference, then you actually see the time information, and then this can be converted to energy and ID of the particle, that kind of information. So, what is plotted here is the energy. So, if you sum up the total energy deposit, you get the total energy, and depending on this Bragg peak height, that depends on the m and z of the substance. So, you can identify, for instance, z equal to 12, which is magnesium, then this is aluminum, this is silicon, phosphorus, and just a few ions of sulfur. So, you basically take the stopping power, which is related to the charge as a function of time, and that is related to the voltage that you get ultimately, that is analyzed, and you can either digitize it or you can do pulse shape analysis and so on. Okay. This is an example of a so-called parallel plate avalanche counter. So, you have this is the cross-sectional view and this is the front view. So, this is something that we made for measurements in the Pelletron Linac facility at TIFR in Mumbai, and basically it uses the time of flight principle to tag so-called quasi-elastic events, which means events where in this particular reaction silicon plus tin, things which are close to silicon come into the detector, but we are interested in evaporation, the process where this goes to 152 samarium, and then that evaporates a few particles. So, particles of the order of 150 or so, where the complete momentum dissipation is there, and so they are slower. So, in the time of flight spectrum, you see them very clearly, and you can distinguish them very nicely from the quasi-elastic. And this is of course set up where you have a beam coming in, you have the target, and this is the place where this annular PPAC is placed, and this is done in coincidence with BGOs and a high energy gamma ray detector. So, you can see when we did this experiment also with a germanium detector once, and you can see this is the line coming from the evaporation residue. So, this is gated with the quasi-elastic, you do not see any structure, but gated with the evaporation fragment residues, you find peaks which are clearly visible. This is also shown in the multiplicity spectrum. These BGOs, 38 in number, closely packed hexagonal detectors. They measure how many gamma rays have been detected, so we call that a fold, and you can see that without this gate you get this kind of a fold distribution, whereas if you put this fragment residue gate, which is emphasizing the evaporation kind of channel, then you find a multiplicity distribution which is consistent with that of the compound nucleus and a few evaporated neutrons and so on. So, this is used to clean up the spectrum and look at things that are of interest for that particular experiment. Okay. This is a time projection chamber. This is, as I said, the modern cloud chamber. So, this was invented by Nygren, and this is a Lawrence Berkeley report. In fact, there is handwritten things on this report in 74, as early as 74, but it really came into vogue in the 80s, and basically it consists of a cylindrical geometry. You have a plane where you have a cathode, so this is where the ions, positive ions drift, and the electrons drift in the opposite direction towards the anode, and this is symmetric with respect to the center. So you have electrons drifting this way and that way. Only one part is shown here. So here you have on one end you have a so-called pad plane. Now this can be wire chambers, it can be silicon detectors and whatnot. But the idea is that you get X and Y position information from these pad detectors, and the Z information comes from the time evolution of this pulse. Okay. So if it is a particle that's, say, primary ionization here, then it moves faster, and if it is somewhere here, it takes a longer time. So the Z information comes from actually the time information. So you have X, Y, Z information, and of course, if you have an array, then the whole track can be mapped. And so this is a electronic version of the cloud chamber, you might say. The timing reference comes from scintillation photons in PMTs, or it could be even in gas detectors and so on. And the time projection chamber, of course, can be operated both in the gas or liquid phases. In the gas phase, of course, you can have various gases. In fact, in the neutrino-less double beta decay experiment on xenon, I think this uses a gas phase, high pressure gas phase detector, whereas in a neutrino detection at Dune, which is a long baseline neutrino experiment, Fermilab to an underground laboratory, there you use liquid argon detectors, each of size about 17 kiloton, but that is because the neutrino is hard to detect. Another example of the so-called time projection chamber at the Large Electron Positron Collider, this is one of the detectors. There are 4 detectors. This is one of them, Aleph, and this is an event display where you have several particles coming out and they can be tracked. And this looks very much like a cloud chamber photograph, right? Except that it is much faster and it gives you much more you have all this information digitized and stored and for later analysis. And of course, in this detector you have a magnetic field as well, so the particle trajectory is curved depending on their momenta. This is another example of an event display in another detector from the STAR collaboration, the STAR TPC at the Relativistic Heavian Collider in Brookhaven from gold plus gold collision. So you can see particles, d by dx as a function of momentum. Very beautiful textbook example of a d by dx curve versus momentum. The references are all given below. Then we come to scintillator detectors. Scintillators are basically materials that emit light if radiation is incident on them. So you produce ionization, then these electrons actually excite electronic states in that scintillator. In sodium iodide, for instance, the energy lost by an electron to produce one scintillation photon is of the order of 25 eV. So 25 eV produces a visible photon, let's say, which is 1/10 of the energy. In a typical plastic, the energy required is about 4 times higher, and so this of course leads to some poorer resolution in energy for a plastic. But these are much cheaper, of course, than crystal, inorganic crystal scintillators. Scintillation photons are detected by PMTs, photomultiplied tubes, with diameters which range from very small diameters of the order of a centimeter or sometimes even less to as large as 55 centimeters. This was built for the Kamioka experiment, the proton decay experiment by the Japanese, and then you also have other photon detectors such as silicon pin diodes, then silicon PMTs in the modern times, and typically these gains range from 10 to the power of 3 to 10 to the power of 7. This is just to show you that there are a large number of scintillators. Sodium iodide was probably one of the early scintillators that was used in energy measurements. Of course, zinc sulfide is also a scintillator, but that was used more just to detect an event, and this was used in fact by Geiger in experiments which are suggested by Rutherford for the alpha scattering experiments that showed that the nucleus is much smaller than the atom. Okay, so there are various cesium iodide, calcium cesium iodide pure, which is very fast, the bismuth germanate, barium fluoride, and the most modern one, of course, is the lanthanum bromide cerium doped scintillator, which gives something like 61,000 photons as compared to sodium iodide, which is 38,000 photons per MeV. There are other scintillators also which give, you know, in this range of tens of thousands and are fast and so on. So, this is just to show you the range. These are organic scintillators, there are some plastic, these are the numbers correspond to the numbers which the company has given for this, but you can typically see that you have about 10,000 photons per MeV in these detectors. Some also have pulse shape discrimination. So, for instance, this last one has pulse shape discrimination, you can use it to distinguish electrons and recoil protons. This is just another picture where fewer scintillators are listed, just to see that there is a range of densities. Bismuth germanate has the highest density of about 7. Decay times vary from, for instance, barium fluoride is a fast component with 0.6 nanosecond decay time, and then there are very slow ones like the cesium iodide, which has a decay time constant of 1000 nanoseconds. And then, of course, the number of photons per MeV is given here. Also, they have different spectra, intensity as a function of wavelength. Some are hygroscopic, some are not, some are cheap, some are ultra fast, some need a UV glass and so on. So, these are various kinds of detectors have various properties, and you have to adapt to whatever physics you want to do and whatever, of course, money you have. Okay, then we come to semiconductor detectors. So, pure semiconductors such as silicon, high purity germanium are widely used in nuclear and particle physics. Silicon is, of course, much more used in particle physics. High purity germanium and silicon are both used in nuclear physics. As I said already, they have band gaps of the order of 1.1 and 0.7 eV, and you have to use a PN junction. So, you operate this in reverse bias, and typically the volume that you have removed the stray electrons from is of the order of size of the detector itself. In general, silicon detectors have a small volume as compared to high purity germanium detectors, which are used for gamma ray detection in nuclear spectroscopy experiments. The low Z of the silicon detectors and small volume in planar geometry enables particles, charged particles to be detected, but it has relatively much less sensitivity to photons and neutrons and so on. High purity germanium detectors come in shape, various geometries, planar and cylindrical. This is the planar geometry and this is the cylindrical geometry. For instance, you can see a comparison between gamma ray spectra. This is for cobalt 60 source. You have these very narrow peaks in the germanium detector, whereas in the sodium iodide you have much broader peaks. So, you can see that high purity germanium, which gives resolutions of the order of a couple of keV at 1 MeV, and sodium iodide typically has about 70 to 80 keV at 1 MeV. This is one of the configurations of high purity germanium Clover detectors. That means 4 detectors in one vacuum enclosure, and this is at TIFR. This array actually moves around the country and 3 different accelerator laboratories to do nuclear spectroscopy experiments. Then the latest in this business is the so-called gamma ray tracking high purity germanium detectors, because gamma rays interact via multiple Compton scattering in germanium detectors. So, for energies of the order of 100 keV or greater. Now, for lower energies, of course, the photoelectric effect dominates and the whole energy is deposited in just one go. Whereas for higher energies, then there can be multiple scattering, and so you don't know where this interacted from. And this is especially important when you have a Doppler profile to the gamma ray peak. For instance, that is shown here in this particular reaction. You can see that the original has a very broad energy distribution. In this case, for instance, is of the order at 800 keV or the order of 30 keV. But once you correct for the fact that it has interacted at a certain place, and that can be done by these tracking arrays, then you can get back a narrow peak. Okay. So, when this recoil velocity is of the order of a percent, of the order of percent or even larger, then the Doppler spread is greater than the resolution of the high purity German detector. So, you are not actually making use of the power of the high resolution detector. So, this led to the development of these tracking arrays, and what happens there is you have multiple segmented detectors, and you can tell where the first interaction took place by looking at the pulse shape that you get. You can have either a single kind of anode or cathode where you pick up the pulse, or you can have that also segmented, and then ultimately you can find out what is the first point of interaction, and this is shown here. If you can see, this is the first point of interaction, and you can see that that can be pinned down to a few millimeters, okay, 1 or 2 millimeters. So, that tells you that where it has interacted, and then you can correct for the you can say that this is the primary vertex, and then you can add back energies corresponding to coincident detector events, detectors which fired. So, you can add these multiple Compton scattered gamma ray information, and from the first point of interaction you know where it has occurred. So, you know the theta, so you can correct for the Doppler shift. This is the reference given below. This is in this Nuclear Physics News, which is actually a very nice, freely accessible, and this is a review article in that. Next, we come to the cryogenic bolometer. This is a very interesting concept. When a charged particle interacts with matter, it produces, of course, electron hole pairs or electron ion pairs and so on, but ultimately all that energy is dissipated in the form of heat. Now, of course, for room temperature devices, this is not easily sensed, okay, because the temperature rise is very small as compared to the temperature itself. But if you go down in temperature to millikelvin, then the specific heat of the detector or the material of the detector actually decreases, and in case it is, for instance, an insulator, then it goes like T by theta d, where theta d is the Debye temperature, to the cube. So, you can see that as compared to, let us say, 300 degrees, if you go down to millikelvin, then that is a huge factor. So, CV becomes very small. So, even for a very tiny deposit of energy, you get a measurable increase in the temperature of the substance. And so, this is a setup at the Tata Institute, which was built to actually try to measure neutrino-less double beta decay in 124 tin. So, this is the cryogenic part, and this is the control part. So, the idea is like this, that if you have an absorber, then this produces heat, and then you have a sensor which actually measures the increase in temperature. So, of course, you have to calibrate this detector at that low temperature and so on, and then this heat is actually dissipated to a thermal bath at this temperature, and you get a thermal pulse, the delta T as a function of time, like this, and the time scale here is of the order of hundreds of milliseconds. This is taken from a thesis of Vivek Singh written up in 2014. However, of course, you can also, just as you have an insulator, you can also use a substance that goes superconducting, and then if you go below the superconducting transition temperature, then the specific heat goes like exponential minus T by theta g, where theta g is the gap energy. Okay. So, you can use either insulators, or you can use something that goes superconducting, and in either case the specific heat will come down drastically, so that any small heating up you will be able to sense the temperature rise. So, these are examples. This is an example of a large cryogenic bolometer that was used to search for neutrino-less double beta decay in 130 tellurium. This is called QOR, and this is about 742 kgs, several about 1000 tellurium oxide crystals. the specific heat at 10 millikelvin is such that it gets you get a 100 microkelvin rise per MeV deposit in one of these crystals. This is the picture, a cutout of the bolometer, shows feed throughs, cryolines, heat shields and so on. So, you go right from 300 Kelvin to 10 millikelvin here. Okay. This is a spectrum in the region of interest where you have the two betas and neutrinoless double beta decay that you are searching for. This should have been the peak. So, from this kind of spectrum you can put a bound on the the neutrinoless double beta decay, and they are constantly improving this. So, and taking more data. So, hopefully we will see neutrinoless double beta decay in this case, else we have put the best bound that can be put, and this would probably go either way in deciding the physics of neutrinoless double beta decay. So, this is the reference given here, and of course, there are several references in that which tell you about the apparatus and so on. Okay, the basic electronics that is related to detectors, I have just summarized here in a slide. Of course, electronics is much more complicated than what is depicted here, but a typical detector charge signal is small. For instance, the minimum ionizing particle in a 100 micron silicon detector produces only charge of signal of the order of a femtocoulomb. So, you have to do things to, you have to have low noise amplifiers, but if you have a gas detector or some other detector where you have charge multiplication, then of course, you get gains of the order of 10 to the 3 to 10 to the 7, and then the electronics becomes somewhat simpler. The detector signal is amplified using either charge sensitive or current sensitive or voltage sensitive preamplifiers, depending on the kind of signal that you have and the processing that you want to do. Then the most modern method now is use fast sampling ADCs right from 10 megahertz sampling frequencies to 10 gigahertz, or it can go to a timing discriminator if you do not care about the information that is there in this signal. You just want timing information or want to have a trigger condition, and then this digital information is examined in real time by a trigger logic unit. There can be several levels of this logic, level 1, level 2, level 3 in the biggest experiments where you have huge amount of large number of detectors, millions of channels. Then you may even go to level 3 where you reduce the number of selected events such that they become manageable and they can be stored for offline analysis. Of course, some of them you would like to sample so that you can monitor in real time how the detector is performing. So, in summary, we have seen a very brief overview of particle detectors. We have seen some examples of detectors, both small and large, and also just a glimpse of what kind of electronics. Perhaps we will come to that sometime later, because electronics is a whole subject, so is the data acquisition and simulation. We might come back to that in a little more detail at some later time. Thank you.